The next talk, now the next talk um, by Professor Andrei Dikarev, parallel spinors on Lorentzian Weyl spaces. Please, let's begin.
So my name is Andrei Dikarev. I'm a PhD student in Masaryk University in Brno, Czech Republic. I have a talk today for in the topic parallel spinors on Lorentzian Weyl manifold. I think I need to turn on my camera. Why not? Oh. So first I will give a definition of parallel spinor on pseudo-Riemannian manifolds. Then I will give definition of weighted parallel spinors on Weyl manifolds. Then I will talk about the holonomy on the Weyl manifolds in Lorentzian signature. Then I will introduce the Kuhn and Walker structures for this manifolds and a local structure on these manifolds, which admits parallel spinor. And in the end, I hope I will have enough time to talk about Einstein-Weyl equations. So spinor structure on pseudo-Riemannian manifolds. Suppose we have a oriented pseudo-Riemannian manifolds, MH of signature RS, and denoted by PSO, the bundle of oriented orthonormal frames over M, and its structure group SO RS. Let lambda be the two-fold covering of SO by spin RS, and we say that the pseudo-Riemannian manifold admits a spin structure per spin if there exists a lambda reduction of the bundle PSO to a bundle per spin. Denoted by delta RS, the standard spinor model. Consider the oriented pseudo-Riemannian spin manifold and let the spin be the lambda reduction. The associated vector bundle S, given by this formula, is called spinor model or spinor bundle. Denoted by nabla S, the connection on this bundle, which is induced by Levi-Civita connection, nabla H, and nabla can be given by this formula. And we have the important relation between the holonomic groups of the connection nabla S and the Levi-Civita connection nabla H. Here I will give the definition of parallel spinors. A non-trivial spinor field is called parallel if nabla S of C is equal to 0. And we have the following fundamental principle, which says what the space of parallel spinors is isomorphic to the space of the spinors at the point, which are preserved by the holonomy group of nabla S. And if we have a simply connected manifold, then the space of parallel spinors is equal to the space of spinor at the point which is annihilated by the holonomy algebra of the connection nabla S. Parallel spinors are special Killing spinors which represent supersymmetry generators of supersymmetric field theories and supergravity theories. So it's kind of difficult to explain, but there are some applications in physics, especially in supersymmetry theory and supergravity theory, but I'm not into detail, so I'm sorry. If you will have additional questions about application in physics, maybe I can answer. So first I will provide the known results and The first of them is parallel spinors on Riemannian manifolds. We have a theorem proved by Wang. Let MH be a simply connected, complete, irreducible Riemannian spin manifold with parallel spinor. Then its holonomic algebra is one of the following. What types of algebras we have? And the next theorem gives a description of parallel spinors on Lorentzian manifolds. The theorem says, suppose we have an undecomposable Lorentzian spin manifold Mg of Lorentzian signature 1 n plus 1, which admits a parallel spinor. Then its holonomic algebra is a product of H and Rn, where H is a direct sum of the same for algebra as for Riemannian case. Now I'm going to give the definition of the manifolds. Suppose we have a triple MC nabla, where M is the smooth manifold, C is a conformal class of pseudo-Riemannian matrix of signature Rs, and nabla is a torsion-free affine connection on M, such that for each metric from the conformal class, there exists one form omega, such that this relation holds. I will note here what the metric from the class and the one form omega determine the connection by this formula, where K is a tensor, and we have the following relation on this tensor K, given by this formula. Now I'm going to fix some notation. We will denote by C spin the product of R plus and spin, and CO is a R plus and SO RS. We have a twofold covering, lambda C, and for oriented Weyl manifold, MC nabla, let PCO be the corresponding bundle of oriented conformal frames. And we call a spin structure on the Weyl manifold MC nabla is a lambda C reduction of the bundle PCO to the bundle PS spin. We will say what KW is a spinor representation of the group C spin RS on the spinor model with weight W, if KW is defined by this formula, where A is from R plus, H from spin group, and C is from spinor model. And the following associated vector bundle is called spinor bundle with weight W. My lecture is has a lot of frames, but I will skip all of examples and corollary. I hope I will have enough time to finish at 20 minutes. Okay, I will continue. The connection nabla induces the connection nabla S on this space SW, and the connection is given by this formula, where G is a metric from the conformal class and omega corresponding to one form. And again, as for the pseudo-Riemannian case, we have the relation between the holonomic group of connection nabla S and the holonomic group of a connection nabla. Definition of weighted parallel spinor of Weyl manifold. The spinor Psi of weight W on M is called parallel if, again, nabla S Psi is equal to 0, and we have similar relation between the space of parallel spinors of weight W. So this is a fundamental principle. but now it's for not parallel spinors for subdominion manifold, but for weighted parallel spinors on Weyl manifold. This is a difference. And we have a similar relation if M is simply connected. Known results. The first one provided by Mariano. He considered only non-closed Weyl structures in Riemannian signature, which admits a parallel spinor, and he showed what the manifolds which admits a parallel spinor exist only on manifolds of dimension 4. The killing spinors are this, which can be described as a generalization of a parallel spinor, was considered by Buchholz. I won't speak about this too much, so I think it's enough to note him here. And the most closest to my result is results obtained by Messin, Orkin, and Paloma Lozano. They considered the Weyl Lorentzian manifolds, but they considered only Einstein-Weyl manifolds, which immediately give the restriction on the weight of parallel spinors. And me and my supervisor, Anton Galayev, we considered the general Weyl manifolds. So we obtained the classification of parallel spinors of every weight and every dimension. So in this paper, they very carefully studied the manifold of dimension 4 and 6. So to continue, I need to provide some notation. We will denote by C or 1 n plus 1 the conformal Lorentzian algebra, which is given by this sum. We suppose what Weyl structure is non-closed. It means what nabla G is not equal to 0, but it's given by the formula above, where nabla G is equal to omega something. So we fix with basis of Minkowski space, and we will denote the subalgebra of a Lorentzian algebra, which preserving the null line Rp by this, and this subalgebra can be identified with the matrix Lie algebra. And we will denote the element of the algebra CO 1 n plus 1 Rp, the conformal Lorentzian algebra which preserves the null line Rp. We will use the notation for elements of this algebra B, A capital X, where the B is from R and this triple is from CO Rp. The next two theorems give the recently obtained the classification of holonomic algebra of non-closed Weyl manifolds in Lorentzian signature. I think that's not important here, but it will be used in the proof of our results. So I will skip them. And our result, which gives the classification of the holonomic algebra for the Weyl manifolds, which admits the parallel spinors. I will read the theorem. Suppose we have a Weyl manifold of Lorentzian signature, then it admits a non-zero parallel spinor of weight W, if and only if its holonomic algebra is one of the following. So the classification consists two types of algebra. Here, K and H are the holonomic algebras of Riemannian spin manifolds carrying the parallel spinor. And if you don't understand this notation, I will provide here the matrix form of these algebras. I might have only 5 minutes. How is it now? The dimension of this algebra are provided on this frame. Again, I think I don't have enough time to go into detail. So the dimension is obtained. I think that's enough to say here. So the definition of Kuhn and Volcker metric. Suppose we have a space Rn+1 and consider coordinates of this kind on it. And the metric given by this formula, where H is a U family of Riemannian metrics and A is a one form. Then the metric G is called Kuhn metric. If functions Re are independent of the coordinate V, then G is called the Volcker metric. And some additional property which I will skip. Now, suppose what we have Lorentzian Weyl manifolds, which admits a parallel distribution of null lines, which means the holonomic algebra is contained in CORP. And we have a theorem which describes the local form of the manifold. Suppose we have a Lorentzian Weyl manifolds of dimension n+1, admitting a parallel distribution of null lines. Then, locally around each point of M, there exist coordinates and the metric G, such that G is a Kuhn metric. So I will return to this slide. Kuhn metric where H is a U family. But H does not depend on V, which is the idea. And the corresponding one form omega satisfies this relation. Additionally, if the manifold satisfies the additional conditional on the curvature, then we have a finer description on a local structure. The theorem says if we have a Lorentzian Weyl manifolds of dimension n+1 and which admits a parallel distribution of null lines, which will be denoted by L, then connection nabla satisfies this condition, and around each point there exists a local coordinates and the metric G, which is Volcker metric. So the one form A will be does not depend on V. Moreover, we can choose the coordinates in such a way that A will be equal to 0. I will skip the proof, but it's not quite straightforward, but I don't have enough time for this. I think I don't need this theorem here. And another result, I think I will end here after reading this theorem. Suppose we have a Weyl manifold of Lorentzian signature, which is given by the triple MC nabla, and suppose it's simply connected and the structure is non-closed, then this manifold admits a non-zero weighted parallel spinors of weight W if and only if the holonomic algebra H of a connection nabla G epsilon, or my mistake. I skipped the definition of nabla G epsilon. Sorry for that. Does it make sense to continue? But what this theorem says, then the holonomic algebra of the connection of this connection is the holonomic algebra of a Riemannian spin manifold admitting a non-zero parallel spinor. And locally around each point of M, there exists local coordinates and the metric given by this formula, where H is a function and H small is given by this formula, and H does not depend on V, and corresponding one form satisfies these conditions. So this theorem gives the local description of Weyl-Lorentzian manifolds with some additional conditions. This is, I think, some corollary and examples. I don't need them, and I don't have enough time for Einstein-Weyl equations. Never mind. I think I will stop here. Any questions?
Thank you. So any question or comments? No comments.
I should apologize.
Sorry, one question.
Yeah.
You said that more conveniently considerate equation Einstein with dimension is equal to 6 more than which when the dimension is equal 4. Yeah. More
No,
convenient
I said what previous result obtained by give me a second.
Einstein-Weyl. Yeah.
I said what the dimension 4 and 6 was already studied.
Yeah.
Is that the question? So have I answered?
No question, no comments. Thank you very much. Thank you. Thank you, applause.
Thank you for attention.
Thank you.